Tonight on the Astronomy Show, we take a look at the new IMAX film, Destiny in Space, and you could win 2 tickets to it. Don't run yet, the universe is not shrinking. I repeat, not shrinking. Chris Gainor speaks with Canadian astronaut Roberta Bondar about her flight into space. And we have David Dodge with Astro News.
Welcome to the Astronomy Show. I'm Chris Gainor, and this show will feature Destiny in Space, a spectacular new IMAX film which is now showing at the CN IMAX Theatre at Canada Place. This film, which is produced in Canada, takes us not only inside and outside the space shuttle, it takes us to Mars, Venus, and to distant galaxies. We'll be talking to one of the stars of Destiny in Space, Canadian astronaut Roberta Bondar. We'll also have our Astro News and an interview from Victoria with Dr. Peter Stetson, who will tell us about the latest findings about the age of the universe. Stay tuned for more details about how you can win one of 2 free sets of tickets to Destiny in Space. For more information about Destiny in Space, call 682-IMAX. And now, our presentation on Destiny in Space.
In the history of human exploration, explorers went out, and either they went alone or they went accompanied by very few people, and we on Earth only learned afterward, and rather remotely, what their experience had been. With IMAX, now we go with the space explorers, and we really go with them. The whole of the Earth is sort of beside them as they do their exploration in space. And this has never happened in human history.
Destiny in Space differs from the other 2 space films we've made, Dream is Alive and Blue Planet, in that it takes people on a much longer journey to places that they couldn't possibly go before now. That is namely to other planets.
In Blue Planet, we took advantage of that position in space that the shuttle gives us to look down at our planet and learn about what's going on our planet. And in this film, we take advantage of that same position in space to look out into the solar system and out into the universe.
Yes, sir, you have go to seat.
Something very big is going to happen, and something very big is going to happen to you. And so you kind of hang on. You hang on to your seat and you hang on to your heart. Because things are going to happen.
3, 2, 1, 0, and liftoff.
As the orbiter lifts off, you can feel all the shaking, you can feel all the power behind you, you can see the steam and exhaust as it comes up around you, and then the shuttle starts climbing very rapidly, and you have this tremendous sensation that you're going up an elevator that's shot through the roof and is going to continue forever.
There's been some hot news in astronomy lately. You may have heard of recent results from a team of mostly Canadian astronomers that cut the size and age of the universe in half, or so the story goes. That's perhaps not quite what happened, but we're going to talk to one of the team members to find out what did happen. Their research concerns the scale we use to measure the size of the universe, or at least one of the scales we use. Distances are often the most difficult things to determine in astronomy, and there's really no single way of measuring distances in space. We have to use about half a dozen different methods, and most of them aren't terribly accurate. One of the better techniques involves a certain type of star called a Cepheid variable. This is a rare type of giant star, maybe 25 or 30 times the size of the sun. They're unstable. They pulsate in and out like immense beating hearts. They come in a small range of sizes, but the bigger they are, the longer they take to pulsate. Nature seems to follow a fairly strict rule here, with the biggest Cepheids taking a few months for a complete cycle, while the smaller Cepheids bounce in and out in only a few days. So if you find a Cepheid variable star, you can tell how big, and therefore how bright it must be, by simply timing it. You compare this with the brightness you observe, and then a little high school mathematics will tell you how far away the star must be to appear as faint as it does. At least that's the idea. And it works pretty well out to the distances where you can't see individual stars, even giant ones. It's that limit which has just been pushed back significantly. That's where our guest comes in. We have with us Dr. Peter Stetson of the National Research Council Hertzberg Institute of Astrophysics Dominion Astrophysical Observatory in Victoria, BC. Hello, Dr. Stetson. Welcome to the Astronomy Show.
Hello, thank you.
When Hubble was discovering Cepheid variable stars in nearby galaxies way back when Jan Oort was in knee pants, what's so new and special about your team's discovery?
Well, we have been able for the first time, I'm actually on two teams. One team that used the Canada-France-Hawaii telescope on the big island of Hawaii, and a completely different team that has been using the Hubble Space Telescope to measure the distance to the Virgo cluster of galaxies. Now, astronomers pretty much agree on the distances to things within our galaxy, and we pretty much agree on the distances to the nearest dozen or so galaxies. But by the time you get beyond the nearest dozen or so galaxies, there is a controversy over the scale of the universe. And the Virgo cluster of galaxies is the biggest milepost just beyond the point where the distance scale becomes controversial. So determining the distance to the Virgo cluster will start to resolve the controversy about the large distance scale of the universe.
Now, there has been a lot of argument about the rate of expansion of the universe, which is another thing that comes out of the kind of work you've been doing. Astronomers have argued for years whether the speed was down around 50 or up around 100. Your team has come up with a value of around 87 kilometers per second per megaparsec in the grand units that are applied to this kind of study. What does this say about the age of the universe, and why is that making some astrophysicists uncomfortable?
Well, it's causing a serious problem, because once you know how fast the universe is expanding, which has been known for a long time, and once you know how big the universe is, which is what we're settling right now, you can calculate how old the universe is from a simple model. You compare how big it is with how fast it's growing, and you then have an estimate how long it has taken to grow from 0 to its present size. This turns out to be somewhere in the range of 8 to 11 billion years. This is a problem because another thing that we can measure the age for are star clusters. And there are some star clusters in our galaxy whose ages have been reliably measured to be 15 or 16 billion years. Now, it's absolutely impossible to imagine a universe which is younger than some of the things that are in it. So either we'll have to abandon what we thought we knew about the way stars evolve, or we'll have to abandon the simple model of the expansion of the universe and adopt a more complicated model. This is something which we've known was possible for a long time, but nobody has wanted to do it. We always like things to be simple.
Well, what side are you betting on? Who's going to blink first here, the cosmologists or the stellar theorists?
I think the cosmologists are scratching their heads a lot harder than the stellar theorists are right now.
What plausible resolution could you imagine coming out of this?
Well, back when he invented the general theory of relativity, Albert Einstein included a term in one of his equations called a cosmological constant. Later on, he regretted introducing this and said that it was probably the biggest mistake of his career. But now it looks as though we will need this cosmological constant in order to describe the more complicated expansion of the universe. It looks as though the expansion of the universe has been accelerating since the beginning. It hasn't just been coasting apart, it's being pushed apart by something called the vacuum energy, which is what this cosmological constant describes.
That would be a wonderful irony if Einstein's major mistake turned out to be thinking he'd been mistaken.
Yes, that's a very good irony, I think.
Now, scientists using the Hubble Space Telescope have just announced a rather similar result on a neighboring galaxy in this same cluster. How does it feel to scoop a team that's using billions of dollars worth of equipment?
Well, I'm scooping myself because I'm on that Hubble Space Telescope team.
Nice way to hedge your bets.
Well, I think we have to recognize that the Canada-France-Hawaii result was Alexander Mackenzie sort of stuff. It was exploration. They said it couldn't be done. We tried it and we managed to do it. but I think that's not really the way to continue. The Hubble Space Telescope, on the other hand, is a team of surveyors. They're moving in, they're doing the job right, they're going to map the universe, and they're going to do it with high precision, precision that simply could not be achieved even with the best results from CFH on the ground.
It certainly was a magnificent technological achievement that you've done. Exactly how did you achieve it? Using ground-based equipment with a great hazard of being underneath the atmosphere. You didn't have the advantage of being in space. What sort of gear were you using, and who developed this?
A team of scientists and technicians led by Robert McClure of the Dominion Astrophysical Observatory and by René Racine of the Université de Montréal developed a special camera for the Canada-France-Hawaii telescope that actually takes some of the shimmer of the atmosphere out of the image before recording it on a detector.
Now, most of the follow-up work of this you're predicting will be done by telescopes in space, predominantly the Hubble telescope.
I think that's the way to go, yes. We can count on the Hubble to make an accurate measurement. With Canada-France-Hawaii telescope, it was barely possible, but it would have been a tremendous amount of work to get the accuracy that will be easy for the Hubble. I think we should let the Hubble do what it does best and let the Canada-France-Hawaii telescope go off and tackle the big problems that Hubble can't touch.
Well, what is next then for the team that developed this remarkable high-resolution camera?
Well, they have already built and installed a second-generation high-resolution camera on the Canada-France-Hawaii telescope. They are now finishing the construction of a third-generation camera, and we are in the process of designing fourth-generation cameras for the Gemini telescopes that will become operative at the end of this century.
That must be a mouth-watering prospect. You're going to be able to get some genuinely enormous optics to work with.
I certainly hope the committee accepts my applications for observing time, yes.
Well, we'll certainly wish you luck on that. It sounds like fascinating work and certainly turned a lot of heads in the astronomical community. Thank you for sharing your results with us, Dr. Stetson. Good luck on future researches.
Thank you very much.
I really enjoyed the film. It was great to see it. I was part of the team that worked on the backpainted astronauts, so it was great to see what went on. It's so close up what went on right there.
Oh, I think some of the Hubble stuff, some of the Hubble repair shots were wonderful, really, really interesting.
Oh my goodness. You know what? I like the surface shots of Venus and Mars. I thought they were fascinating, and I'd like to see more surface shots of other planets. It was wonderful.
Working with a 90-pound camera in zero-G, I wondered before we flew how that was going to be, how that was going to work, because when you come in to train us, you guys can lift up an elephant, and you walked around with this camera and put it on dollies and rolled it around, and here we were going to be in zero-G. It was my first flight. First time to use this camera was also my first flight.
We usually have about 25 hours of training time to get them up to speed to where they can load the camera, change film, learn how to take light readings the way we like them to take light readings, let them learn how to shoot IMAX as opposed to shooting video or 16 film, which they're accustomed to shooting, because it's totally different shooting for IMAX than it is for any of these other formats. The astronauts are really good students. They're quick learners. They pick up things technically, particularly, very quickly. It's tough for me to stay ahead of them a lot of times. I'll put the camera down and they'll be playing with it and have it loaded before I can show them how.
And it was actually pretty easy to use in zero-G. In fact, a whole lot easier than it is on the ground, because you can just let go of it and it stays put.
Took about 3 years to train for, and so the IMAX was a part of it the whole time. And it takes crew members to train on the average of 25 hours per crew member to train for an IMAX flight.
Did you have any particular problems when you were shooting it?
The difficulty with the IMAX camera from taking video pictures, for example, is there's no automatic focus, and you have to measure the distance. Of course, the operator's floating and the subject's floating, and the distances change. So it's much different trying to take a picture, and people who normally work in the shuttle, astronauts, are not professional photographers. I mean, the great shots we had from the outside of the silent were all done remotely from the IMAX personnel on the ground. But the ones in spaceflight, we're dealing with people who have been suddenly trained to now think like a photographer, and sometimes we had a bit of problem with the lighting or motion or things being out of focus, but those were all taken and dropped on the floor.
Did you grab a pair of binoculars and look up in the sky?
Yes, we had gyro-stabilized binoculars on our flight so we could hold them up and they'd be nicely balanced. And we used the stars for alignment of the shuttle. So people are always looking up and they're focusing on various constellations to line up in various stars for the star sensors. For me, I was kind of trying to pick out Mars and pick out Mir from the actual stars. Because on Earth, too, you have to be trained to do it. And, you know, most amateur astronomers understand how difficult that is to try to explain to a neophyte.
What was your favorite part of the film?
There were so many really great parts. I mean, the initial launch sequence was wonderful. But I guess my favorite shot has to be where the SPA satellite actually came across the orbiter on the arm, and you can see the shadow, and it came down in front of the word Discovery right on the orbiter's side. And that was the ship I was on, so you know, you fall in love with your ship. And it was just, I mean, that's what we looked like when we were hanging out there.
Before we start identifying the things in the nighttime sky, I thought we'd just review the phases and positions of the moon for this month. The phases of the moon are, on Thursday, last Thursday, the 3rd of November, we had the new moon. Now on this new moon, the moon went directly between the Earth and the Sun, causing a total solar eclipse. Now we have a new moon every month, but not every new moon causes a solar eclipse. This eclipse passed across South America from Peru to Brazil. Now we have an agent down seeing the eclipse, and next month John Tanner will be in to describe the eclipse and show us some of his pictures. First quarter will be on the 9th. And on the 17th, the moon will be full. Now we have a very special treat in store for you on the full moon because we're going to have a lunar eclipse. Now it's not going to be a total lunar eclipse, it's a partial lunar eclipse. And you have to have very sharp eyes to see this one because the moon only just skirts through the outer edges of the Earth's shadow. Starting at about 8:30 in the evening, the moon will start going into the Earth's shadow. But I don't think you're going to see anything till about 10:30 or so when the moon is deepest inside the shadow. And the eclipse is over at 2 minutes past 1 the following morning. On the 25th, we have last quarter moon, and we get back to new moon on the 30th. As the moon goes around the Earth, it appears to pass by all the planets in the nighttime sky. I say appears because the moon is much closer to us than the planets are. On the 11th, the moon passes by the ringed planet Saturn, and on the 25th, it passes by the red planet Mars. The moon passes by all the other planets as well, but they are either too faint to be seen or too close to the sun for safe observing. Last month I mentioned the Orionid meteors, or shooting stars that would appear to come from the constellation of Orion. Well, in November we have a meteor shower coming from the constellation of Leo the Lion, called the Leonids. Now the Leonids are very special because every 33 years the Earth passes through a particularly large mass of meteoric material. The last time we went through this mass was in 1966, so we're hoping for another big meteor shower in 1999, when literally thousands of meteors will be seen. Now, on November 17th, when we are in the middle of this particular meteor shower, it's also the night of the full moon, so I don't think we're going to see too many meteors. The sun has had more than its fair share of spots these past few days, and because of that, the National Oceanographic and Atmospheric Agency has issued a number of aurora alerts. Aurora borealis, or northern lights, are greenish gray colored lights, curtain-shaped things that are close to the northern horizon. But sometimes when we have a very particularly bright sunspot, we'll have a very dynamic northern light display. Sometimes they'll be red and directly overhead. Again, you won't see them unless you get out and observe the nighttime sky. So we encourage you to do that. If you're out and about between the car and the house, take a scan of the nighttime sky. While scanning the skies, see if you can spot a few of the stars and constellations they make up. Directly overhead is a group of 5 stars that make the loose letter W. This is called Cassiopeia. Traditionally, Cassiopeia is a queen sitting on the throne, but we see the letter W. Below Cassiopeia, towards the south, are 4 widely spaced, moderately bright stars that mark Pegasus, the flying horse. Now, I don't think you're going to see a horse, flying or otherwise. What we normally see is a square of stars, and we call that the Great Square of Pegasus. Below Pegasus are 2 bright stars, one not too far from Pegasus and one much closer to the southern horizon. That star that's close to the southern horizon is called Fomalhaut, the brightest star in Pisces Austrinus. And the star that's closest to Pegasus, that's no star at all. That's the planet Saturn. Returning back to Pegasus, go to the upper left-hand corner star. Now, to the left of that star are 3 fainter stars. If you take a pair of binoculars and center the middle of those 3 stars, then slowly pull your binoculars north, you'll pass by 2 fainter stars. Stop on the second fainter star. Just above and to the right of that star, you'll see a hazy patch of light. That is the Andromeda Galaxy. The Andromeda Galaxy is 2 million light years away from us. That means that the light you see tonight, or whenever you observe the Andromeda Galaxy, left that galaxy 2 million years ago. Rising in the east, you should be able to pick out Orion the Hunter. Orion the Hunter is easily spotted by looking for 3 stars that are equally bright and equally spaced, and these are his belt stars. He has stars for each shoulder and stars for each kneecap as well. The shoulder stars are Betelgeuse, the brighter star, Bellatrix, the fainter star. His kneecaps are Syath, the fainter star, and Rigel, the brighter star. Over in the west are the constellations Cygnus the Swan and Lyra the Harp. And Lyra the Harp is noted by the bright star Vega, very close to the northwestern horizon. Cygnus and Lyra are constellations that belong to the summertime sky. Cassiopeia and Pegasus are constellations that belong to the fall sky, and Orion belongs to the winter sky. So at a single glance, you can see all 3 seasons at once. To finish our exploration of the nighttime sky, I'd like to introduce you to the standard yardstick that every astronomer uses to pace off the nighttime sky. The hand. Provided you have a fist to clench, a clenched fist at arm's length subtends 10 degrees of arc. The pinky and index finger stretched out like this, 15 degrees of arc. And these 2 fingers together are 5 degrees of arc. This is a useful bit of knowledge when you're trying to explain where an object is in the sky, how far 2 objects are away from each other, what directions an object's traveled. Because at the planetarium, I get lots of phone calls from people describing objects as being as big as a dinner plate. In my home, I have dinner plates in 3 different sizes, but a clenched fist will always describe 10 degrees of arc. I'll be back next month to help introduce you to some of the new things and new discoveries in astronomy. For the Astronomy Show, I'm David Dodge.
The final sequence in Destiny in Space, the service mission for the Hubble Space Telescope. This is the mission that will repair the optical problems with the mirror and bring up to date other mechanisms aboard the Space Telescope.
Coming up.
You are not working on your lawnmower. You could be, but you are not. And the fact that you are working on the most powerful instrument in the world, but also something of incredible beauty, when you are working on something which is already of that beauty, you know, it gets you. It gets your heart and soul. So it's not just being a craftsman to fix something in that kind of way, but you are working on something and with something that is that beautiful. And also the kind of play which is going on in the head. You've got this extraordinary, beautiful Earth. You got a beautiful spaceship, but you're also thinking of what Hubble brings back to humanity in terms of aesthetics. It is not just science.
In this film, we leave Earth altogether and visit other planets for the first time. And that is an experience that nobody has had other than the astronauts who've gone to the moon so far. You'll see the surfaces of Venus and Mars in extraordinary soaring flyovers. You'll see the globe of Jupiter in detail that no one has ever seen it before, in motion.
You look at all these stars and think, we have just scratched the surface in our destiny in space. I mean, surely our destiny is out there someplace.
The preceding program was produced through the facilities of Rogers Community 4, Vancouver. We want to hear from you and invite you to leave your comments and suggestions on our 24-hour response line message machine. Please call 731-5812.